Okay. Yeah, I think we can start now then. Hello, guys. Good morning. It's my pleasure to introduce Dan. The speaker for today is going to talk about lines on the cubic surface.
Okay. So today I want to present to you guys, not really a proof, but more like the ideas contained in the proof of this really nice theorem that's in algebraic geometry. So let's write down the theorem. So let's let S be a smooth projective surface. I'll define all of these words eventually. Be a smooth surface, cubic surface. Be a smooth cubic surface in P3. Okay. Then S contains exactly 27 lines. So I'm giving you the punchline before I tell the joke, but this is just a cool little result, right? I mean, any cubic surface, whatever that is, surface defined by a cubic polynomial, contains exactly 27 lines all the time. As a quick note, algebraic geometers like to study algebraic geometry over weird base fields, right? So we could have fields of characteristic P, but for the talk, we're just going to focus on algebraic geometry over the complex numbers, okay? Make things a little bit easier. I think basically everything I say will carry over to this characteristic P case if you care about that, but except for like a couple statements, but slight modifications. Yeah, okay. So let's define some of these terms, smooth cubic surface, P3, what's a line, right? So we can get a feel for what we're talking about, and then I want to talk about the ideas that go behind the proof of this thing. So first thing that we should talk about is probably projective space, okay? So projective space is something maybe we've all seen before, I don't know. So projective space Pn, this is the set of lines through 0, through the origin, in Cn plus 1. Okay. Right, we define an equivalence relation on Cn plus 1, where we say any vector is equivalent to a scale of the same vector. Okay. On Pn, I'm going to talk about a little bit why we like projective space in a moment. But for now, let's just accept the fact that we have this projective space, and we can do algebra on it, or algebraic geometry on it. How do we do that? So on projective space, I don't know how to spell anything. On projective space, we have what are called homogeneous coordinates. So these are just the coordinates induced by Cn plus 1.
I'm sorry, Dan, can I ask a dumb analyst question?
Yeah.
By lines through Cn plus 1, you mean complex planes, yeah?
By line, I mean complex lines. So Cn plus 1 is a complex vector space. So these are the one-dimensional subspaces of Cn plus 1. Yeah. Okay, so by coordinates induced by Cn plus 1, what does this mean really? It means they look like this. So x0, x1 to xn. I'm putting these little colons here to really emphasize the fact that these are homogeneous coordinates and not actual n plus 1 tuples, because something like this and something like this these define the same point. in Pn, right? So if I consider these as just n+1 tuples, so actual vectors in Cn+1, then these two things lie on the same line for all C in C. They lie on the same line, and so when you go down to projective space, they actually define the same point, right? So these are what our coordinates look like, okay? Now, if we want to define an algebraic variety contained inside a projective space, what we need to do is we need to use polynomials that are sort of compatible with these homogeneous coordinates. Okay, so to do that, we use homogeneous polynomials. I don't know how to spell anything. Okay, so what's a homogeneous polynomial? F of x, maybe, so how do I want to do this? So f of x0 to xn is a homogeneous polynomial. Equal sign is homogeneous if all of the terms are of the same degree. Okay, so for example, f of xy being x squared plus xy plus 3y squared, this is a homogeneous polynomial, right? All of the terms have degree 2. Oh, my bad. This is degree 2. Okay, now, I don't know how to stop that from happening. Okay, so this is what a homogeneous polynomial is. The reason we care about this is because homogeneous polynomials of degree d, so if f is homogeneous of degree d, then they have this very nice property that f of x0, or f of, maybe I'll write c times x0, cx1, cxn. This is just c to the d times f of x0 up to xn. Right, I factor out the c to the d from every single monomial term, and this is what we get. And so what this means is that, so maybe not the value of f as a polynomial is invariant under scaling, but the set on which f is 0 is invariant under scaling, right? Invariant under scaling, which means that we have a well-defined 0 set inside a projective space. Okay, so a projective algebraic variety is one of these 0 sets, or an intersection of these 0 sets, if you will. So I'll just write a variety in Pn is the 0 set of some collection of polynomials. Some polynomials. Okay. So when we talk about varieties, this is what we're referring to. And because we're doing this over the complex numbers, we can sort of use our intuition about manifolds to think about what a variety is. And really a variety over C it's basically a manifold. So it's a manifold with maybe some self-intersections and maybe some singularities. By singularities, I mean like cusp points or something like this. Okay. Right. So a couple things that I want to say about varieties. First thing is I want to define what it means for a variety to be smooth, right? So this theorem that I want to talk about says that we need a smooth projective surface, right? A smooth cubic surface. So what does it mean to be smooth? So a variety, X, is smooth if the Jacobian of its defining polynomials has full rank. So it's smooth. Its defining equations has full rank. Right, so this is, I mean, this is the same definition in the study of manifolds, right? I mean, this is the implicit function theorem or something like this, or implicit function theorem, inverse function theorem. I don't know. Right. So this is our definition of what it means to be smooth, and in practice, what this means is that the thing that we're actually looking at is a manifold. Okay. Okay. So there's this, and now I want to talk about degenerate varieties or reducible varieties. Okay, so a variety is reducible or degenerate. I'm going to use either terminology here. If it reduces as a union of subvarieties. And I'll give some examples. Okay, so first off, the pictures that we sort of have in our heads, right? We're not thinking about pictures in complex n space, right? That's too hard. So the pictures that we have in our head are usually the pictures in real space, all right? So whenever we're talking about stuff, I want you to think about lines and surfaces in like the real plane or in real free space or something like this. So some examples here. What does it mean for a variety to be reducible? Here's something which is irreducible. So it's going to be cut out by x squared plus y squared, just in the plane, okay? So I don't want to think about homogeneous polynomials or anything like this. I just want to get a sense of irreducibility. X squared plus y squared equals 1 gives me this circle, right? And this is something which is irreducible because I can't factor this polynomial x squared plus y squared equals 1 down any further. And you see the circle is sort of contained as a single piece. Maybe I'll even omit these lines because we just have the circle. Something which is reducible is, say, something like xy equals 0. So this is the union of these two lines, right? So these are both what are called conics, plane conics. Conic just meaning they're degree 2 polynomials, okay? But one is a union of two lines, two degree 1 curves, right? And so in this sense, the two lines is sort of a degenerate case, okay? And so I want to keep that in the back of our mind for a little while because that'll be important later, okay? Yeah, okay. So why do we care about projective space? Okay, so the reason we want to do this, we want to prove this theorem in projective space, it's a little harder to visualize because projective space sort of twists around on itself in a weird way, but it has a lot of nice properties. So one thing, it's the algebraic analog I can't talk and spell at the same time. It's the algebraic analog. Of compactness. Okay, we have a lot of very nice results that hold only for projective varieties that are similar to compactness results we have in topology. So for example, if I defined a map between two algebraic varieties, then the image of a projective variety is always a projective variety. Similarly to how the image of a compact set is always compact, right? So we don't really need to worry about things going off to infinity because we always have our points at infinity or our lines at infinity and so on. The other thing is that intersections are nice. Okay, so what do I mean by this? You know, I could, maybe I don't want to say that. So what do I mean by intersections are nice? I mean, curves and surfaces and things like this, they always intersect in the way that one would sort of hope for when we're studying polynomials. So for example, two lines always intersect at one point. This is one example, a line and a conic. So line and conic intersect at 2 points. And then there's an asterisk here, it's with multiplicity. So I'll just write with mult. So I need to specify this because of course I could have like a circle and then a line tangent to that circle. It intersects the circle at only 1 point, but that point has multiplicity too, right? And then if I move the line away from the circle, then I have to say, okay, well, this line actually intersects the circle at 2 complex points somewhere. So, you know, the pictures don't always work out, but everything always intersects in sort of a nice way. I guess I should point out that this is in the plane. Right, in general, if I'm in 3 space, I can always have 2 skew lines, right? So 2 lines don't have to intersect in 3 space, but a line does always have to intersect a plane, right? In P3, a line intersect a plane is 1 point. Similarly, a conic intersect the plane is 2 points. Again, with multiplicity, maybe. What else? So a plane intersect a surface. Gives us a curve. A curve. And what is the degree of this curve? It's exactly the degree of the surface. Degree of the curve equals the degree of the surface. So for example, 2 planes always intersect as a line. A plane and some kind of degree 2 surface will intersect as a conic curve. A plane and a degree 3 surface will always intersect in a cubic curve, right? The key is that this curve may be degenerate. Okay, so when I say this, I mean, like we said, a degenerate conic curve, for example, might be two lines, the union of 2 lines. So if I intersect a plane and a degree 2 curve, it might intersect not as a circle, but as something like 2 lines, right? Similarly, when we intersect a plane and a cubic curve, we might get 3 lines, okay? And this is, we might get 3 lines, or we might get a line and a conic. So we want to keep this in mind, okay? So I sort of just threw a bunch of definitions at everyone. But I'm hoping that at least the statements sort of make geometric sense. Maybe these intersections are a little mysterious, but they sort of work out because, you know, we're over an algebraically closed field or whatever. Okay, so I want to move on now and actually get to the point. And I could do that if my notes were in order. Okay. So let's move on to the point, unless anyone has any questions. Feel free to interrupt me if there are questions. I'm sure we all know this by now. Okay, so on to the point. Which is the proof of this theorem, right? Okay, so a smooth cubic surface, which is a surface defined by a cubic equation in projective 3 space, should always have 27 lines. Okay, so let's let S be our surface, our cubic surface. In P3. Okay, say S is defined by the equation f of x, y, z, t equals 0, where this is homogeneous of degree 3. That's what a cubic surface is. Now I'm gonna maybe, I don't know, we'll see how you feel about this. Maybe this is a cop-out. I want to suppose that S has a line. Actually, that S contains a line. Okay. Maybe this is too much, but this is always true, in fact, and we'll prove it later if we have time. Okay. So I want to suppose that S contains a line L. I'll call it. Contains this line L. What can we say now about the lines on S? Okay, well, I mean, if I have another line on S and it has nothing to do with L, maybe L won't give me too much information. So what about the lines on S meeting L? So can we find the lines on S meeting L? This is the question. And the answer is yes, right? So if I have 2 lines, then 2 lines always make a plane. Or they span a plane. They determine a plane. Right? I mean, this is just the same, like if you draw 2 lines for me and they intersect in R3, right, they give you a plane. And it works the same here. So 2 lines, 2 intersecting lines. 2 intersecting lines will always determine a plane. So what that means is that if I take planes containing L and I cut S with these planes, I should be able to detect the other lines meeting L, right? They'll be contained in these planes. All right, so because of this, we're going to consider planes P and the intersection P intersect S. Okay. So what does P intersect S look like? Okay, well, like I said before, planes meeting cubic surfaces always give you cubic curves, right? The thing is that we know that our cubic curve, we know that this plane intersect this surface contains this line. So L is contained in here, and this is a cubic curve. that means that this cubic curve is degenerate somehow, right? It contains a line. So that means it has to be a line plus a conic. Okay, so there are two cases. In case one, so this curve is this line plus this conic over here. Maybe I'll call this L and I'll call this C. This is a conic and this is a line. Right. And then in case two, this conic C is also degenerate, maybe. So we could have three lines. Maybe this is L and this is R and this is S. I don't know. Okay, but these are basically our two cases. We either have a conic and a line, or we have three lines. And so the part that I care about is, okay, when are we in case two? So right, that is, when do I have a plane which intersects my surface with only lines, right? Because this is what's going to give me the lines intersecting L. Okay, so this is the question, and you know, it is sort of a little intimidating. I mean, like, how could we ever tell what this conic looks like by intersecting with this plane? And the answer is, you know, we're doing algebraic geometry. We have a bunch of polynomials, so we can do some algebra with these polynomials and we can make some deductions, okay? So let's, for the moment, so let's just suppose that L, the line, is given by the equations z equals t equals 0. So these are two linear equations, z equals 0, t equals 0. Those define two planes. So when I set them both equal to 0, that's the intersection of the planes, I get this line, right? And I can do this just by a change of coordinates. Right, I can rotate my projective space around somehow and maybe get that this line actually has these equations. That doesn't change anything. My surface is still cubic and all this, right? So I do this just so we can talk concretely about these planes, right? So our line L is given by these equations. What does that mean about our planes? Well, our planes now can only have the variables z and t in their defining equations if they contain L, right? Otherwise, if I just set z and t equal to 0, then that wouldn't be enough to guarantee that I lie on the plane. So the equations for planes containing L only contain z and t. All right, I mean, now these are linear equations, right? Homogeneous linear equations in two variables. That means they have to be of the form P. So this is my plane P. And they have to be of the form mu z equals lambda t. These are what my planes look like. Right? Okay, great. So how much time do we have left? We're at 11:33. Oh, good. Okay, I'm about on schedule. Okay, so our planes look like this. Now we're actually getting somewhere now. What we can do is suppose that we're on the plane, right? Now, if I suppose that I'm on the plane, then what I can do is I can substitute in some coordinates. So, right, I can replace z with lambda t maybe, or maybe I can replace t with mu z or something. Substitute this in for the equation for s and figure out what this conic looks like, right? So what does that look like? Well, if suppose mu doesn't equal 0, right? So what I can do is just set mu equal to 1 by division, right? And get z equals lambda t. Okay. Great. So we have this. Now my equation, what did we call it for s? F. Called it big F. Maybe that was a poor choice. I'm going to call it little f. I'm going to use big F later. So this is little f of x, y, z, t. So I'm going to rewrite f. That's not how you spell this. F x, y, z, t. We're going to rewrite this as a of z, t, x squared plus b, y plus bxy. Let me write this down correctly. Bxy plus cz plus cy squared plus d of I want to make sure I get this right. Don't mind me. I'm just forgetting what I wrote down. Plus b or plus dx, right? Plus ey plus f. Okay, so remember, this is supposed to be a homogeneous polynomial, right? So all of these terms have to have degree 3. So what this means is that a, b, and c are linear in z and t. D and e are quadratic in z and t. And then f is cubic. In z and t. Right, and I can do this because when I set z and t equal to 0, that means I'm on my line, and my surface needs to contain my line, right? So when I set z and t equal to 0, I should be able to, I should satisfy the equation for f, and so I should be able to get it into this form. This is the only way I'll be able to do that. If I have some terms with some x's and y's by themselves, those won't be 0 when I set z and t equal to 0. So I wrote a of zt here, and I didn't write b of zt, but this is a b of zt, and this is a c of zt, and so on, right? I just want to make that absolutely clear. So I have a bunch of different polynomials in z and t. And now what I can do is, since mu isn't equal to 0, so z equals lambda t, I can replace z with lambda t, right? Replace z with lambda t. So what do I get? I get a of, so for example, I get a of lambda t, t, right? And I get b of lambda t, t, lambda t, t, and so on, right? Now remember, these are homogeneous, and so they're invariant under scaling, right? So I can take this t out. So this is actually the same as t times a of lambda 1. And this is the same as t times b of lambda 1, right? Similarly, when I have d of lambda t, t, this is t squared times d of lambda 1, because d is quadratic, right? And for f, I get a t cubed. Okay, so we have this. This is what happens when we restrict to the plane now. We have restricted to our plane P, and we've restricted this equation to our plane P. So let's see what it looks like, okay? So substituting everything in, what do we get? We get a of lambda 1. So I'm just going to write a and B and C and so on. So we get A times T times, I want to do this quick, A times T x squared plus B T xy plus C T y squared plus D T squared x plus E T squared y plus F T cubed, right? Where this is A of lambda 1, B of lambda 1, and so on. So these are just numbers depending on lambda. Okay, this looks like the equation for the conic, right? I mean, we're close. The thing is that there's a t in every term. So when we divide out by t, right, the t is in every term because this thing contains the line. The line is z equals t equals 0, but we've set z equal to lambda t. So when t equals 0, we're on the line. So when we divide out by t, we get ax squared plus bxy plus cy squared plus dtx plus ety plus ft squared. And this looks like a conic, right? This is a quadratic polynomial, right? So and this is the equation for our conic, right? If we set this equal to 0, we will get the rest of the intersection, which is exactly the conic. So I want to know when this conic degenerates into two lines, okay? And it turns out the conic degenerating into two lines is the same thing as the conic not being smooth. So what I need to do is I need to take partial derivatives and check my gradient of this defining function. Okay, so to check degeneracy, I don't know if I spelled that right, check smoothness. Okay, so what do my partial derivatives look like? I mean, for this thing, maybe I'll call this g, little g. So g of x is 2ax plus by plus, I don't know, d, right? G of y is bx plus whatever, right? We can compute this very easily. It's just derivatives. But the thing that we notice maybe after we write this down is that we can actually write it like this: g of x, g of y, g of z is equal to this matrix: 2a, b, d, b, c, e, d, e, f. And actually there's a 2 here and a 2 here, right? Times, oh, there's a t, x, y, t. We get this sort of matrix looking equation. Now, the reason I say this is because, okay, well, I want to know when the conic is singular, when the conic is not smooth. So I need to know when this is 0, which means that this matrix has a kernel, which means that it has 0 determinant, right? So the actual condition that we have to check for this conic to be lines is this determinant equals 0, right? And this is about as far as I want to go. So what we can do is we can actually take the determinant and we get that it's a degree 5 polynomial. Okay, right, remember we have a variable lambda in here, so it's actually det of lambda. Right. So it's a degree 5 polynomial, so it's 0 exactly 5 times. with multiplicity, right? So now we have to do some sort of analysis of this polynomial. We have to check that it doesn't have multiple roots and things like this, but we can do all this and we get that it vanishes exactly 5 times, right? Exactly 5. After checking that it doesn't have multiple roots, right? Which is great. That means that we found all of the lines meeting L. We found that there are, when we cut S by planes containing L, exactly 5 of those planes will contain other lines. Okay, so let's summarize everything that we've just done right here. Okay, so if L is contained in S, then there exist exactly 5 planes containing L, containing L, such that P cap planes P. 5 planes P containing L such that P intersect S is equal to 3 lines. Right. Okay. What can we say about these lines? Okay. Well, they all intersect each other. What I mean by this is when I have for a particular plane P, for a particular P with P intersect S equal L1 union L2, or maybe I'll write L union L prime union L double prime, right? L intersects L prime. So L cap L prime is a point. L intersect L double prime is a point. And L intersect L prime intersect L double prime is a point. Because these are all lines contained in a plane, and so they always intersect each other, right? So we have this. So they all pairwise intersect. Okay, so now I'm gonna write these down as 5 distinct pairs. We're basically done with the proof. We just need to count lines now. Okay, so we have for L, so associated to L. To L, we have 5 pairs of lines. L I, and I'll write Li prime. So for I equals 1 to 5. Right, such that L, Li, Li prime all pairwise intersect. Furthermore, is this necessary? Let me think. Yeah, I think so. We need also, right, Li and Lj can't intersect. Equals the empty set, right? I think we need this. So the reason for this is just that if I have L here, and I have Li here, and I have Lj here, then that means that they're all contained in a plane. Right? But the plane containing Li and the plane containing Lj are different planes, right? So this is a contradiction. Right. So that means that we always have this. Okay. We've established all of this now. Now we can actually just count the lines, okay? So let's let P let's let R, S, and T be lines contained in a plane. R, S, T contained in S be lines in a plane. Because we have 3 of them, right? We've supposed we have a line, and so I can take one of these planes and I'll just say R, S, and T are L, L1, and L1 prime. Okay, then we can form our pairs for each of these lines now. We can form the RIs and the RI primes, the SIs, the SI primes, and the TI and the TI primes. Form the RI, RI primes, TI, TI primes, SI, SI, SI prime. Right, so remember, we have exactly 5 planes doing this for each of them, but one of them is this plane containing R, S, and T. So we actually only have 4 of these. Okay. These are all of the lines on S, is my claim. Okay. So first, if I have another line, if L is any other line, so I'll call this plane P, is any other line on S, then remember, lines always intersect planes, then L has to intersect P. So this can't be empty. Right, but L is contained in S, so it intersects actually P intersect S. L intersect P intersect S. This is non-empty, but P intersect S is just R and S and T, right? This is R union S union T. S maybe is a little choice, a bad choice here, but it's a little S. So L actually meets one of S or U or R or S or T, right? L meets R or S or T. So that means that L is actually in one of these lines, in one of these pairs that we've already constructed. So these actually are all of the lines on S. And now, I mean, we just need to check that these lines aren't the same. But again, for the same reason as right here, maybe I'll emphasize this, the purple star or something. For the same reason as right here, if RI and SI were the same, for example, then they would all be then R, S, and RI would all be coplanar. But that's bad because the planes defining this is different from the plane defining this, right? So none of the RIs and the SIs are the same. In the pairs are the same. Are the same. And now we just have to count. Right? We have R, S, and T, that's 3 lines. And then we have our 4 pairs, so 8 of the RIs, 8 of the SIs, 8 of the TIs. That's 3 times 8, which is 27. And that's it. Right. So this is it. I mean, we suppose that there was a single line. We intersected the line with some planes, found that there were exactly 5 planes with which we could get other lines. And then from this, I mean, it was just a matter of counting, right? After we had that. Yeah. So maybe it's probably better to end early. I could maybe let me say a little bit about how we actually get a line on S. All right, I don't want to elaborate on this too much. So to get a line, to prove that S has a line, how do we do this? We form what's called an incidence variety. Okay, so what we do is we let G be the space of lines in P3, and we let P be the space of cubics in P3. Okay, and now, so we can figure out what these things are actually, but I don't really want to talk about that. So now what I can do is I can form this incidence variety inside of G cross P. Okay, this incidence variety is defined to be the set of pairs LS such that L is contained in S. Okay, now this is non-empty, right? If I take 3 planes, for example, that defines a degenerate cubic surface, but a cubic surface nonetheless, and it certainly contains some lines. So this is non-empty. Okay, so now what I want to do is consider this map to P. So, right, P is this thing right here. So this just maps LS to S. And the question is this surjective? Okay. Well, after doing some thinking, and actually reasonably elementary thinking that I could outline it here if I had time, we can get that these are both 19-dimensional. Okay. And so to check that this map is surjective using some theorems from algebraic geometry, it actually suffices to check that the fibers have to be 0-dimensional. Because these have the same dimension right here. And then to check that the fibers have 0-dimensional, we can black box some other theorems of algebraic geometry, and we actually just have to check that a single fiber is 0-dimensional.
Are these spaces compact?
Yes, they're all projective, actually. This is actually a projective space. And then this is a Grassmannian, which is actually contained inside of some big projective space. So yeah, they are compact, if we want to say this. So we just have to check that a single fiber is 0-dimensional, which means that, so a fiber is 0-dimensional, that means that there are only finitely many lines contained in that surface, right? The fiber over a surface is the lines contained in that surface. So we just need to find a single surface containing only finitely many lines. And this is pretty easy, actually. We can write one down. So in C3, x, y, z equals 1 contains no lines. And then if we look at infinity, this amounts to setting x, y, z equals 0, contains 3 lines. So this is a cubic surface which contains exactly 3 lines. And the funny thing is that this surface is actually not smooth. So what we've done is we've proven a theorem about cubic surfaces, about smooth cubic surfaces containing lines. And the only actual cubic surface that we had to write down was not one of these surfaces that we're talking about. Okay, that's all I have to say, I think. So.
Cool, thank you, Dan. So thank our speaker. Okay, are there any questions for Dan?
That was a really nice talk, Dan. I have more of like a comment rather than a question. In the determinant part, you can see that you need to work over an algebraically closed field. because you say this degree 5 polynomial has exactly 5 roots.
Right. Yes.
So it's really nice that you can see that as well.
Right. I actually wanted to, so sometimes you might hope that we could get it so that all of these lines on this cubic surface have real solutions. So there are points which have coordinates which are all real, and we can actually, and I found a little picture online, which I need to find now right here. So this is like a nice little animation of one of these surfaces. And here are all of the 27 lines. And actually you can see a little bit, I lied to you at some point. So I said that the 3 lines have to intersect in a triangle, but this is not actually the case. They can all intersect at a single point. But I wanted to streamline this talk a little bit. So these black points on this little animation denote the points where 3 of these lines intersect. Yeah. Are there any other questions?
Do you know if this was like the original proof? I don't know if that's like if the question really makes sense, but
I don't know if this was the original proof. I think this proof, I mean, I said in the abstract, I just took this off of Wikipedia. The proof was proven in the theorem was proven in 1849 or something like this. It's a little unclear to me. I mean, this sort of seems to me to be elementary enough. Well, okay, this proof that we have just done, if we suppose that a line is contained in the surface, seems elementary enough to have been come up with then. The proof that S contains a line, maybe not so much. So I think that you can actually do some pretty long and tedious but very elementary algebra to get that S contains a line. Yeah, and so this is probably what they did. This is in Reed's book, I think, the undergraduate algebraic geometry. It's a couple pages long, proving that S has a line. It's actually kind of, yeah.
Yeah, it was nice. I haven't seen this before, so that was really nice.
Okay, thank you so
Nice.
much, Dan. That was really cool.
Yeah, of course. Okay.
So I guess we can end here for today then. So thank you again, Dan, and thank you everyone for showing up. And we'll see you all next week.